Okay, thanks to the organizers for inviting me, and thanks for putting together this very nice meeting. I'll speak about exceptional field theories, which we have seen in the morning and also beginning of the afternoon. And we have seen exceptional field theories are attached to various exceptional groups. In fact, the structure differs. The structure is slightly different if you choose different exceptional groups. And what I want to talk is about the particular case where your group is in fact a fine algebra. So just to put a little bit of context within supergravity, these exceptional field theories, as we saw, try to make manifest the exceptional symmetry groups which you find in supergravity theories after dimensional reduction. So most of this you have seen this morning already, but let me just give you a few key words. So that's the work of the 80s in supergravity, the observation that whenever you reduce high-dimensional supergravity on a torus, you find a lower-dimensional theory which has a very large global symmetry groups. And for example, reducing 11-dimensional supergravity on the 7 torus gives you a 4-dimensional supergravity which has a global E7, the famous work by Kremer and Julian. And what exceptional field theory does in supergravity is reformulates these higher dimensional theories such that the E7 does not come out as a mystery, but it sort of manifests already in the formulation we have given of these theories. And then some keywords which we have seen today, which is like the basic structure of these exceptional field theories. The underlying structure are generalized diffeomorphisms which you can define for a given exceptional group. Once you have worked out the structure of these generalized diffeomorphisms and their algebra, which in general is not the Lie algebra, but the Leibniz algebra, you can build invariant two-derivative actions, invariant under these symmetries. Those are, to a large extent, unique, and those unique invariant actions then precisely reproduce the bosonic sector of maximal supergravities. And then without any reference to supersymmetry, so just knowing the bosonic field content and the structure of these generalized diffeomorphisms, in fact, is sufficient to recover the full structure of the bosonic part of supergravity. And then in supergravity, these theories are used as a very powerful tool to construct vacua or to address the questions of consistent truncations of high-dimensional theories down to lower dimensions. Now, unlike DFT, where in principle you can give a kind of universal construction based on the group ODD, in exceptional field theory, depending on which exceptional group you choose, those theories all look slightly different. And that is related to the fact that what you do in supergravity is you take the 11 coordinates and you split them into some external and internal bit. So the external bit is, would be 4 external coordinates if I go from 11 down to 4. So D would be 4, I have 4 x mu's. And the internal coordinate is the one which David was discussing in detail, which I then double in double field theory, or with an exceptional field theory, I would embed them into some really large representation of my exceptional group. And so you see, the lower I go in capital D, so the less external dimensions I have, the more internal dimensions I will have, the bigger my exceptional group is, and the bigger will be the representation in which I embed these internal coordinates. And on that space, then I will put the section constraint to bring them down to the physical space. And so far, these theories that have been constructed separately for all the exceptional groups, one by one, over a few years, until the biggest finite dimensional exceptional group, which is the 8, which is the symmetry of 3-dimensional supergravity, which would amount to 3 external dimensions. So I break the 11 dimensions, 3 plus 8, and the 8 internal, I would embed that into a representation of the group the 8, which is the adjoint representation of the 8 of dimension 248. So all that is well understood. Those E8 diffeomorphisms is what Olaf talked about this afternoon. Jakob talked also about the structure of these generalized diffeomorphisms for external algebras. What I want to talk about is extending that to the case where we make the step from finite dimensional to the infinite dimensional exceptional algebra. So this is the algebra E9, the loop extension of E8. It's the symmetry of 2-dimensional supergravity. So that would amount to a split where I only keep 2 external dimensions, and I would embed my 9 internal dimensions into some infinite dimensional representation of this affine group. So we have to deal with infinite dimensional symmetry algebras, infinite dimensional representations thereof, and so on, but still these are affine algebras, so we know representation theory is under control and all that. Of course, when you see this split and the fact that you have to construct these theories group by group, you're looking for one unified picture which has all of that, and you're sort of tempted to try to make capital D as small as possible and go down all the way to, say, capital D 0, and everything would just be one huge external internal sector. Okay, so that's where we are heading in the long term, but for the moment we just make the step down to still keep 2 external coordinates, so we still are left with an affine symmetry group which we have under control. But we make the step to some infinite dimensional internal symmetry algebra. Okay, so I'll just give you a few key formulas from exceptional field theory, generic exceptional field theory, the generalized diffeomorphisms, the tensor hierarchy, because that's what we want to develop for these affine algebras. And I'll just recall a few facts about these affine symmetries which show up in 2-dimensional supergravity, because that's the one we want to sort of lift up to 11 dimensions. And then I'll go for the construction of an exceptional field theory now based on this affine algebra E9. We will construct generalized diffeomorphisms now associated to that affine algebra, work out the section constraints, the analog of the section constraint now on these infinite dimensional spaces, and finally construct some invariant action functionals invariant under those generalized diffeomorphisms, which then would reproduce high dimensional symmetry. And so this is based on work with Olaf and Jakob, who are here, Guillaume Bossard, Martin Sederwald, Axel Kleinschmidt, Franz Cicerich, and Jean-Luc Inversa. Okay, a few key formulas about exceptional field theory, which you've seen to some extent in David's talk, and Jakob's and Olaf's. That's the general structure of a generalized diffeomorphism. Parameter living, living in some representation of my exceptional algebra. The action on a vector which lives in that same representation is the following: you have a transport term and then a term which carries the derivative on the gauge parameter. And if you expand that, I think this is the form which David was showing this morning. If I spell out what I call Z here, there's the Y which David had on the blackboard this morning. So in fact, such a generalized diffeomorphism is a standard E bracket plus some deviation term. The deviation is captured by tensor Y, and the tensor Y is precisely what encodes the section constraint, which then you impose on all your fields. So the fact that you impose the section constraint makes this into an algebra which closes on all fields satisfying modulo terms which satisfy this constraint. Or yet another version of expanding that same formula is up to the transport term. This Z tensor is nothing but a projector onto the adjoint representation. And that shows you why that structure precisely respects the symmetry structure, it respects invariant tensor of my algebra. Because that is nothing but a rotation, an algebra valued rotation on my vector. So it leaves the invariant tensors of that algebra invariant, unlike normal diffeomorphisms. So the algebra closes up to the modulo the section constraint, as was also already discussed. There are trivial gauge parameters, which have sort of zero action on all the fields. As a result, the bracket which you define from this algebra is non-associative as a Jacobiator, and the Jacobiator itself is a trivial gauge parameter, so everything is consistent as far as its action is concerned. Exceptional field theories have this sort of as the basic underlying structure, and they're just built by a theory which is invariant under those symmetries. Invariant under those symmetries in a local form. Now, local means local. The gauge parameter is not only a function of y, in the sense that these are infinite dimensional diffeomorphisms on that y space, but they should also be local with respect to the external coordinates. In the end, we want to describe an 11-dimensional theory where you make it on all the different coordinates. And so that forces us to introduce, whenever we have derivatives in external space, we will have to put covariant derivatives, and there will be gauge field that precisely gauges the action of these internal diffeomorphisms. That's a way of formulating such line theory from a lower dimensional perspective. So the moment you have covariant derivatives and the gauge field, which would make this action local, you will have field strength associated to this vector field. You can write down the naive Young-Mills field strength. Since your algebra of generalized diffeomorphisms is non-associative, the standard naive Young-Mills field strength is not a gauge-invariant tensor, and you have to correct it by some coupling to a two-form field acted upon by an internal derivative, again with that y tensor. Remember, the y tensor measures the deviation from standard Lie brackets. If I wrote in standard geometry, then this term would not be around, I would just have standard Young-Mills field strength, standard Lie bracket here as a commutator. In generalized geometry, my field strength will have an extra term which couples to two forms, and the whole combination will be precisely a gauge and an object, a gauge covariant object and a generalized diffeomorphisms. That's the type of coupling we know very well from supergravity. The moment we have non-abelian symmetries in supergravity, typically field strength gets Stückelberg couplings to the two forms of the theory. And so these two forms need a very particular index structure. That's something which was mentioned in Jakob's talk. So if vector fields live in, say, representation, a given representation of my algebra, this index labeled by this index M, the two forms, they will live in the tensor product of two such representations, so they carry two of those indices, and then generally they live in some subspace of that tensor product.
So there's hidden projection.
There's
some projection.
There's some hidden projection, but which you can simply put into this. You can say, the projection is encoded in whatever this tensor y is. You remember when David gave y for double field theory, for example, y would just be eta eta, which is a very strong projection. Just means that there's a single two form. Okay, and because this all you see here is in fact PQ contracted to the eta. Okay, so indeed there's a projection in here, but in some sense you should also think of that internal derivative as being part of that projection. So we don't see the naked two form, we see it on the under internal derivative. Absolutely. And that's just the beginning of what then we see as a tensor hierarchy in these theories or in supergravity. So now we have the corrected Young-Mills field strength. This is indeed a covariant tensor with respect to our diffeomorphism structure. But now we have to introduce two forms, so we'll have to repeat the game for the two forms. We'll have to define field strength of that, and non-abelian field strength, and Chern-Simons coupling, say A wedge A cube, and so on. And in order to make that into a gauge covariant object, we again will have to introduce a coupling to the next rank P form, and so on and so on. And that you can do out systematically, and that gives you one by one all the P forms of your theory. So this curly D here is not the same D as here. That's not an exterior derivative. That's really like an internal derivative that would be referred to this term here, an internal derivative which couples to the higher rank form. Again, that's a structure which we know well from supergravity. In supergravity, typically this curly D would be a matrix, which we call the embedding tensor, which Olaf mentioned also this afternoon. That would be a matrix which tells you how this higher rank form couples into the lower rank field strength. Okay? In order to make it a gauge covariant object. And the nice thing in all these theories is whatever form is needed here to make that into a gauge covariant object is precisely the field content which you find in supergravity. So you look at your tables of supermultiplets of what you have at your disposal, and exactly the forms you have are those which you need to construct all this hierarchy of gauge covariant field strengths. And it works the same here in exceptional field theory, based on that diffeomorphism structure as a fundamental structure. It works very nicely until you hit the D-3 forms. D-3 forms are the forms which are dual, on-shell dual to the vector fields. And the moment you hit those, in fact, the standard correction of your field strength is not sufficient, and you have to yet add another correction term in order to make this into a covariant object. So you have to add another P plus 1 form, or it would be a D-2 form, that simply comes algebraically. And that guy, so the form, the d-3 forms come in the dual representation to the tensor fields, because they are on-shell to two vectors. So there will be an extra d-2 form which comes in that very same representation. But it satisfies a number of constraints. In fact, it satisfies the same section constraints as those we imposed on the internal derivatives. But now here this looks less mysterious than the section constraint, because this is more like an algebraic constraint actually on this here. And if you think about the supergravity origin, those fields really are related to the symmetries of the dual graviton in 11 dimensions, which you cannot formulate in a non-linear way without compensating fields. And so that's sort of how there is a reason why at this stage that field kicks in. So, for example, if you would build an exceptional field series for external dimensions, your group is D7. In 4 external dimensions, d-3 is 1, so vectors are dual to vectors. So it's already the Young-Mills field strength, which I gave you in a generic form on the last slide. You would have this correction term, but you would have to supplement this term in order to make it a really correct tensor.
So it's the same B? Oh, that's a good.
It's a different B. And they come in different representations. See, this would be alpha is what I call the adjoint representation of E7, but you would need another set of these guys living the fundamental one, co-fundamental representation. Plus, you see they come on a different footing, so to say, these come under internal derivatives, these just come in. Plus, these are covariantly constrained. That's the form of the algebra. But once you introduce that, this will be again a fully covariant object and so on. Gauge covariant under generalized diffeomorphisms. In 3D, so for the E8 exceptional field theory, the one Olaf talked about, this kicks in already one stage earlier. So you wouldn't see it in the Young-Mills field strength, you would see it on the scalar current. And so your scalar current would carry a covariant derivative with the standard generalized diffeomorphisms. But then you would have this correction term, which means you have to add an extra gauge connection. Now it wouldn't be two form, it would be just one form. You need an extra gauge connection, which is just a shift of this scalar current. And that's precisely the couple of gauge parameters A, B, which Olaf put into that Leibniz structure, which combined with that Leibniz algebra this morning. So in E8, you see the appearance of these extra fields already on the level of generalized diffeomorphisms. And that's why if you would just follow the standard pattern of generalized diffeomorphisms, try to close the algebra of these guys here, they do not close, not even if you impose the section constraint. So in E8 EFT, you see that already, without going to higher P forms, just talking about generalized diffeomorphisms. For the exceptional group E8, generalized diffeomorphism of that group will not close into an algebra. You need to extend that algebra by extra gauge transformation, which go together with this gauge field here.
Can I ask one question? In the just out of interest, in case D equals 4, can it happen that the first B term just vanishes, partial n B? Is that an interesting case? Is that of interest?
How would it happen?
Yeah, I mean, would it be that B is just independent in the n direction?
Depends on what kind of solution you're studying.
That's what I'm asking.
For example, imagine you're just interested in 4 dimensions of gravity. Well, then all internal derivatives are absent. Then this term is not around.
I'm just wondering, because without this term, this takes very for the curve in a V2 algebra.
You mean with a B like that?
With the second B, yeah.
With only the second B?
Yeah.
You see what happens, what typically happens if I do a more interesting truncation of that than simply putting derivatives to 0, I would assign a very particular dependence of this B on the internal coordinates, such that that internal derivative would translate into some algebraic action. And then this term, the resulting term I get from here, in fact, looks exactly on the same footing as that one.
So it is a basic step.
Yes.
Okay.
Yes. And that's precisely the structure you typically see in gauge supergravity. When you look for deformations of 4 dimensional supergravity, they have field strength of this type, with a coupling to 2 form, but not, there's no internal derivative anymore, because we're talking about 4 dimensions. There's just a constant, there will be some matrix, this omega will be some matrix, multiplying those beats. But just in an algebraic way.
Then there should be a V2 algebra connection.
Yes, it's
okay.
Yes. But the high dimension origin of that comes, you could embed all this into some internal space such that whatever that matrix was simply comes by the action of that internal derivative.
So I have a little question. So that capital M on the B sub M,
Yes.
is that a multi-index?
No, that is the, so in my conventions, capital M up, say, is the representation of the vector fields. Okay? And so this is just a form which lives in the dual representation of the vector fields. But it's a single, it's just an index which labels one representation.
Okay, I'm trying to see what Y is in general. So are there statements about Y?
Yes, if you, I have some, let's see here. You see, that is the Y tensor here.
Yeah.
It tells you how my diffeomorphism differs from the standard D bracket. So that's the Y tensor. And in general, it expands like that. Right? So Y is in principle nothing but this adjoint projector. Moduli some just trace term and modulo this term. Okay, so there's a very generic pattern behind that structure. Okay. So here in 3 dimensions, okay, we see diffeomorphisms no longer closed, but actually it's not a mystery. It's precisely the extrapolation of this pattern. And now what we will be interested in is extrapolate this even further to the case of E9. So you see, in E7 you would have extra 2 forms to make up your theory. In E8 you would need extra gauge fields and thus a bigger diffeomorphism algebra. In E9, well, extrapolating that, you would need extra 0 forms. So you would see them on the same footing as the scalar fields. So for E9 EFT you would expect your standard scalar fields, whichever supergravity, whatever supergravity predicts for you. But you would have to extend your scalar fields by 0 forms which live in the co-fundamental representation. And indeed we will see when we try to construct those theories that precisely fields of that type come in. And then you see, here they were necessary. For E8, you saw the necessity just from the diffeomorphism algebra, because without those, the diffeomorphism algebra doesn't close. In E9, these fields are not associated with any gauge symmetry. That's yet another step. We will also have to add extra gauge fields. Right? So we have the standard gauge fields, and then we have to add extra gauge fields in order to make the algebra close. But we will see a change already just on the level of the 0 forms. Okay? So those we will not detect when we start looking at the symmetry algebra. Those we will detect when we start constructing invariant actions. That will not be possible without these extra fields. I have like, what, 15 minutes? Okay, very good.
Is there any relation between mesh fields and the auxiliary fields in super space form? It's just a very naive question.
Not in any direct way. But I agree the way that the fact that they come not on the derivative and so on looks tempting. But at least at the moment we don't have any direct link to that. So just the last ingredient in these theories, once you have set up the symmetries, what is really interesting for you is typically what are the invariant actions. So you have symmetry, now you want invariant action on that symmetry. And typically those are 2 derivative actions, they are unique. So once you impose the symmetry, there's only one type of action you can write down. Everything is specified by the symmetry, and that action then precisely reproduces full 11-dimensional supergravity. So that's one way of writing full 11-dimensional supergravity. It has one piece which looks precisely like 4-dimensional supergravity. Einstein-Hilbert, some coset space, some Young-Mills term. It's exactly like 4-dimensional supergravity, except for all these guys now live on some internal space, so they live in fact in 11 dimensions. And so that is important by the fact that there's also infinite dimensional gauge structure we were discussing, there's this corrected Young-Mills field strength and so on, and that takes care of all the internal behavior, which makes that into 11-dimensional field. And then maybe the most interesting term is what I call the potential here, which would collect all the terms which only have internal derivatives on the M. So that term you wouldn't see in 4 dimensions because the internal derivatives go away. but you need it in order to have this theory reproduce the full 11-dimensional supergravity. And again, like this doesn't look very, very illuminating. The only nice property of this combination is it's invariant under generalized diffeomorphisms. It's a bit as if you would insist to write out the Ricci scalar in terms of derivatives of the metric. You wouldn't see anything about symmetries, but you could check by hand that this is indeed an invariant under diffeomorphisms, and so that might be a nice action. And so it is here, these terms are horrible because they're just, every term separately is of course not at all invariant by diffeomorphisms. There's no connections or anything, but that combination of terms turns out to be invariant, and it plays the role of the internal potential. It's a unique action. It precisely reproduces 11-dimensional supergravity and a type 2B supergravity. Both are in. Depending on how I solve my section constraint, David was mentioning there are two different ways I can put coordinates in order to solve my section constraint. Depending on which solution I choose, this action here is type 2B supergravity or is 11-dimensional supergravity.
So, is there a way to guess those terms? How did you...
Say again?
How did you find this
The potential? Yeah. Well, as David said this morning, you write down all the different possibilities and you check what remains invariant under... Well, that's a brute force approach.
Yeah.
Okay. Of course, you would like to see, isn't there some nicer way of understanding this as some kind of curvature scalar in place? Okay. But typically the way to give some more geometric interpretation to this, to see this as some kind of curvature scalar, that happens the moment you introduce fermions to the theory. Okay. If you introduce fermions to the theory and generalized spin connections and all that, then in fact you can recover this very same expression of these few subtleties as some particular combination of what you would define as a curvature tensor. But as I think you are bound to introduce a fermion structure.
Why do you say that? Why do you need fermions? You can just define the spin connections and covariant derivatives and just define a curvature, no?
You need the spin connection.
Yeah.
Yeah.
The spin connection, you don't need fermions for the spin connection. I mean,
well,
it's the other way around. If you want to introduce fermions, you need a spin connection, but you can't introduce a spin connection without fermions.
yes. I need, but it should act on somebody.
Huh?
It should act on somebody, the spin connection. In the end, I want to get
So
the
you
curvature
say,
as a commutator of covariant derivatives, basically on the fermion.
Oh, it only works if you act on fermions.
Or is it, maybe I don't need fermions, but I need the spin connection. I need the general spin connection.
Yeah, it's also not really the commutator, right?
It's not really the commutator, it's some, yes. That's right. It should be some gauge covariant combination of linear expressions. Okay. So there's a nicer story behind this, or there's a brute force method of just checking its invariant. I'm saying that because for E9, the only way we could find was the brute force method, because for E9, fermions are really very complicated. But it would be very nice to see some more geometric stories also in that case. Very good. So that's a general EFT. Let me give a few ingredients of the E9 structure which we want to implement. Two-dimensional supergravity is very simple. It's just a sigma model coupled with bilateral dualities. That's 11-dimensional supergravity once I compactify it down to 2 dimensions. And it's a sigma model E8 over SO16, and that's not specified the Fermat part. But it has so the off-shell symmetries of that 2-dimensional sigma model is in fact just the target space isometries, which is E8. It's a sigma model, you have E8 over SO16. So E8 isometries. But it has a very remarkable structure. It's an integral model in the classical sense, which means in fact there's an infinite tower of dual scalar potentials. So the first one is very easy to see. You have your target space isometries E8, you have the Noether current associated to that, so you can define a dual scalar dual to that Noether current. In fact, the Noether is conserved, allows you to define a dual. So that's the first set of duals, and then you can, that's only the first step in a hierarchy, you can define an infinite chain of dual scalars. Now the dual to Y1 would be a Y2, a certain grading and go through that, and you come out with a hierarchy of dual potentials. Okay? And each one of these is associated to some symmetry, which you can, some on-shell symmetry you can define on the field equations. And so on the field equations, this E8 in fact enhances to its loop extension E9. So we have an honest action of that loop group on your physical fields on the field equations of supergravity in 2 dimensions. And if you wish, you can sort of write a nice way, linearize that action as really a coset type action on this infinite dimensional coset. SL2 times E9 divided by SL11 over K E9 is a compact subgroup of E9. Now, of course, it's very subtle because E9 is an infinite dimensional algebra. Here it would be like a loop group. So in fact, this makes only sense once I fix a certain Borel gauge in which I only have sort of I kill half of my fields and I parameterize things, say by spectral parameter only in one direction. But then I would encode the full tower of dual potentials into an E8 matrix which depends on the scalar parameter. Think of that as a loop group element of E9. Which carries, if you expand it in the spectral parameter, which carries all the hierarchy of dual potentials. And you could formulate field equations in terms of this object instead of the original physical fields. And they are all related by nonlinear duality equations. So the physical degrees of freedom sit only here, but then you have the full power of dependent fields.
The RNS string is a 2D supergravity.
Say again?
The RNS string is a 2D supergravity.
Yeah.
So is this the kind of
is
this analogous? Like, is that why I was thinking?
it depends what I put as a metric here on the sigma 1. For example, if I were on flat space here, then this tower would be not very interesting because I would have my first dual potential and the next dual would just go back to the original. There's no interesting structure here. The fact that I have a nonlinear sigma model here of this coset space type, the fact that it's an integrable sigma model, really amounts to the fact that I have an infinite chain of dual potentials, all independent. And in fact, it's not just the loop group, it extends with the part of the Virasoro. So there's a Virasoro action of L-1, L+1, L0, the SL2 subgroup of the Virasoro. And they are related basically to an action on this dilaton. The dilaton is a free field, so it also has a dual rope chamber, there's a dilaton and an axion field. And those two together form this coset SL2 over SL11. So that's the symmetry structure of 2-dimensional gravity. And then the only other ingredient we need the symmetries and we need the vector fields, because they will tell us where our coordinates live. Now vector fields, as Jakob was discussing, live in the level 1 representation of E9. There's only one, so that's the basic representation of E9. If you would split it under E8, it goes like that. It starts from a highest rate state singlet, and then it has an L0 grading, and it gives some infinite series infinite tower like that. This is the character, which is a very long function. Vector fields in 2-dimensional are non-propagating, so you never see them when you study solutions of dynamics. But you see them when you reduce known theories down to 2 dimensions. And we will need them because the coordinates should be in the dual representations. The coordinates should be in the very same fundamental representation. So indeed, if I split this not under E8, but say under SL9, that highest rate representation goes like 9 plus 36 plus 126, and you recover the beginning of the chain David was writing this morning, standard 9 coordinates, which bring me up to 11, then 2 form coordinates, 5 form coordinates, and that's an infinite chain, which lives on. So it's precisely the same structure here with all the other theories as well. I'm reminding 5 minutes maybe? 8 minutes, perfect. So we can do generalized diffeomorphisms on that structure and the section constraints. So first, section constraints. Remember, the general form of section constraints is this. Some Y tensor contracting derivatives should eliminate all the fields. So all we have to determine is what is this Y tensor now in this case. What can we say in general? The Y tensor, well, it should, we should specify some sub-representation of that tensor product of 2 derivatives, each one living in the level 1 representation. Tensor product of 2 level 1 representations is a level 2 representation. There are 3 of them for E8. Those 3, and each one, if you work this out, each one of those comes with an infinite multiplicity, which you can count by that L0 grading. And so this tensor product is just infinite combination of those, infinite number of those, and infinite number of those with different zero charges. But there's more structure to that, of course. These multiplicities, they carry representations of the coset CFT E9 plus E9 divided by E9. That's a classic Goddard-Olive construction. So the sum of two E9s of level 1 divided by the E9 of level 2 is precisely the coset Virasoro algebra under which these multiplicities transform. In other words, you have a Virasoro action on these multiplicities. Or in other words, the product of two level 1 representations is the sum of level 2 representations with coefficients given by certain Virasoro representations. And so the fundamental object is a Virasoro generator acting on these multiplicities here. It doesn't touch the level 2 representation, it only acts within the multiplicities. So that's the Virasoro generator, and I call it Cn because I rescale it by a number. And this now turns out the section constraint can nicely express just in terms of that thing. For example, look here for some indices. That is like it's a Virasoro generator. It acts on this tensor product of two vectors. For example, the first section constraint simply reads two derivatives contracted with that Virasoro generator should just be annihilated. And then it goes on. There's one constraint for the C0 Virasoro minus identity plus the permutation operator, that should be 0, and then all the negative C minus n's should annihilate derivatives. That's the choice for the section constraints. It's a good choice because it precisely reproduces all those you know in high dimensions, so you decompose that under all the finite dimensional groups, you will find exactly what you had expected. And furthermore, once we will, in 1 minute, write down the generalized diffeomorphisms, these will be exactly the constraints which tell you generalized diffeomorphisms close. Okay, so let's do this very fast. This is now the form of a generalized diffeomorphism. I just go back to that form of an adjoint projector plus a weight term. I spell that out, that is nicely rephrased in terms of this Virasoro generator. So that would be, in this index-free notation, the action of a generalized diffeomorphism, now an infinite dimensional coordinate representation. As expected, they don't close. We knew already for E8 they don't close. For E9 it should be even worse. Indeed, we need an extra gauge transformation. We need to enlarge that algebra by gauge parameters of this particular form, so they live in a two-index space, fundamental times co-fundamental, and they covariantly constrained with the values. And that is contracted with the Virasoro generator. The structure is very nice once you get used to this notation. Everything is in principle encoded in these Virasoro generators. So you do not think anymore about the algebra itself. Everything follows from the properties of these Virasoro generators which show up in the form of the The algebra closes. There's a nice Leibniz-Lode algebra behind, as Olaf was discussing for E8. Very same happens here for these combining these gauge transformation. It's a non-associative algebra, trivial gauge parameters, non-trivial Jacobi, and so on. Computation is remarkably simply, much simpler than for any of the finite algebras, because all that goes into computation is some very nice computation properties of these generators, which are probably well known for people in quantum groups, some Virasoro relation for these guys acting on tensor production. Okay. But that's not, let me come to the end. The very final step, so we have now algebra. It's exactly in the same framework as all the other generalized diffeomorphisms, but it is based on the highest rate representation of the affine group E9. Last step in that program is now find an invariant action under those generalized diffeomorphisms, because that's what should give you back the solution. And recall, 47, you would sort of write down all these terms and try to find a good combination. So challenge, do the same for E9 now in terms of this group elements. So all these indices are run over the highest rate representation. It's a bit subtle. You have to make sure you are in a gauge such that any term only spits you out finitely many terms and so on. But turns out you can achieve all that. You find a good gauge. Every term, once you have solved the section constraint, spits only out a finite number of terms. You have certain generic contributions which are always there in the potential. Those will also show up here. You have a very specific contribution. That's this index contraction of the current, which shows up for E9. And maybe that's just the last comment I'll make. They are based on this current, which I build in terms of the loop group element. So it's a current living in E8. It's a covariant element that transforms covariantly under the full loop group. But potential also needs a shifted current, in which you shift the generator in degree by a degree of -1. In order to make this into a covariant object, the only way you can do is you have to introduce a new field of that type Km multiplied with central extension. That is a combination which is again a covariant object under the loop. And that's where, at the very last, this field comes in, which we had expected all along from the high dimensional results. You need it in order to define a covariant current which you can then use to build up the potential. I'm not going to any of the technical details when we come to the end. So there's a few other subtleties you have to take care of, but the final result is you can spell out a potential now. It's based on this loop group matrix M, together with this additional field which you need to introduce. It's given as a sum of various terms which we can write down, which look very subtle because they involve infinite sums, but they split out finite terms the moment you have a finite number of terms the moment you solve the section constraint. So that would be the sector of exceptional field theory now, based on the group, the affine group E9. Okay, so that's just a summary of the properties of exceptional field theory. We've done it for the infinite, based on the infinite dimensional algebra E9. And we have a potential which really is invariant under the action of those terms. And it just close with a few keywords of the things which would be nice to continue. Most in particular, going to higher rank algebras, I stopped at E9, because that was already pretty complicated, but it's the first infinite dimensional step. Of course, Jakob was already mentioning the higher dimensional, the higher rank structures should be behind, so at some point we would like, of course, to extend all this based on those many more fundamental structures. Understand section constraints and understand to which extent what we are doing is a reformulation of known theories, or maybe a sign of more fundamental structure. So that's all here. Thank you.
You sort of skipped over Schurz-Schwarz thing.
Yeah.
But can you do Schurz-Schwarz for this E9, so you don't need to do section? Section that have Schurz-Schwarz recursion.
What are you saying, you don't need section?
Well, what I mean is, so I can...
So if I say, yes, I can do Schurz-Schwarz. I can do Schurz-Schwarz for this, and if I do Schurz-Schwarz on those generalized diffeomorphisms, I find exactly the gauge structure of 2 dimensions for gravity, which is a very non-trivial check. Okay. What we haven't yet done, and that would be a, that's here, a prediction for 2 dimensions for gravity. What we haven't yet done, you should take this potential now, again, do Schurz-Schwarz on that potential, and that would predict you what is the potential of 2 dimensions for gravity. You see, all other, I mean, you did a lot of these Schurz-Schwarz things. In those cases, the nice thing was always one reproduces the potential of gauge gravity. It's very highly non-trivial consistency check. In 2D, very little is known about what is the potential of 2D supergravity. In this case, this would be a prediction because nobody knows how to really implement supersymmetry in those theories. Whereas here, this is a construction of the potential without any reference to supersymmetry. So this would be a tool to predict something about 2 dimensions.
So I don't know how the final expression looks like, but it sounds like you're going to have infinite sums involved.
As I said, those are infinite sums.
Yeah.
However, the moment you solve the section constraint, because of course when I write like this, I haven't made manifest, I haven't picked the solution for the section constraint. Okay? But any solution of the section constraint will sort of cut off your coordinates at least at some highest level somewhere. So coordinates live in this infinite dimensional representation, but the solution to the section constraint will pick only, say, up to level 3 or 4. And the moment you know that, that means all those partial derivatives have sort of a cutoff in level. If you combine that with the structure of the expression, you'll see that for a given solution of the section condition, that potential will only spit out a finite number of terms. So although it's an infinite sum in order to make it covariant, once you solve the section constraint, what will survive is only finite number of terms.
What have people thought about quantizing?
Well, so far there's nothing done on that.
When you say theories like this, do you mean E9 or
I mean
exceptional field theory full stop?
Exceptional field theory full stop.
You might want to mention Bossard, Einstein.
Oh, but that's a different, that's not quantizing this theory. That's that's using those formulations to.
Oh, it's a one big diagram.
Well, in some sense, you might hope that this has all the features of two-dimensional field theory, where all the information of high dimensions hidden in the fact that it's a two-dimensional field theory, but with some infinite dimensional gauge structure. And as a two-dimensional field theory, at least at the lowest level, it was an integral field theory. You might hope that if you were just about that, to quantize that two-dimensional field theory, you could use the quantum group structure which shows up. You have the charge algebra, which is Youngian and so on. There's a lot of structure behind it. The question, of course, is how much of that you can still have survive the moment you switch on that infinite dimensional internal gauge. But so far, I don't know what that's.
Is the reduction to 2D still useful for saying something about 4D, say, or 11D? Can you take an M2 solitonic Brownian solution in 11D and see its U-duality transforms from a 2D perspective?
I mean, the moment you write down this EFT, you haven't done any reduction. In fact, when you write that potential, for example, you're still it still describes in fully dimensional theory.
Is it so practical to actually go back to see what one has?
That's what typically we do, at least in the high dimension. That's what has been largely exploited in order to lift up solutions, for example. You have given solutions for dimensions to find where it comes from. To embed some low dimensional theory into some high dimensional theory. That's precisely what you can do in these formulations. Now 2D, that has not yet been applied. But in say 3 or 4D, that's exactly what this typically is used for in supergravity.
All the 4Ds, I mean, all the 4D ones, we've got all of the half BPS brains with 11 dimensions. Essentially, these momentum modes in the hidden space. Although you split the space, you still got the both pieces there. It's full of different dimensions. It's so trivial.
Yeah.
Do you see more than was visible in 11 minutes before? Right, I think for
Well, that is the question. To which extent can you, if you take that section constraint the most conservative way and you say we want it in a strong fashion across all the fields, then or to 10. But that's all this question here. Can you make some interesting structure where you weaken that constraint?
So generalization by.
Well, if I may, I think you'll see more exotic brains in the sense that you can do more twisting. I mean, it depends whether you think exotic brains exist already in supergravity.
Yeah.
So if you want to make honest exotic brains, you need the extended field theory. And because you've got so much more extension, you can construct many more exotic brains of this, we could say E7 or SL5.
Yeah.
So in that sense, the exotic brain twisting is much richer, perhaps infinitely richer.
is that an expectation or is it no?
I mean, let me be careful what I say. Let me say expectation.